Good afternoon, class. Today we're going to continue talking about Chapter 7. This is Chapter 7, Part 2. Please have your calculator, pen or pencil, the pre-printed notes or paper to write on, and your periodic table. We are going to start by talking about a way to count small particles such as atoms, molecules, and ions. We use a number that we call the mole. Please don't be scared by the mole. It is just a name for a number. Just in the same way that the word dozen is a name for the number 12. Right? If you go to the store and ask for a dozen donuts, you're asking for 12 donuts. You could also use other names for numbers, such as a ream of paper is 500 sheets, or a case of pop is 24 cans. It's just a name for a number. In this case, this is a very, very large number, 6.02 times 10 to the 23rd. We gave it a name because saying 6.02 times 10 to the 23rd every time we mean this number is a big mouthful. And as I said, this is a very big number. If you were to write this number out, it would look like this. 1, 2, 3, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Very big number, right? Why do we have such a very big number? Well, because we're talking about atoms, molecules, and ions. Atoms, molecules, and ions are really, really tiny. If I asked you to go into the lab and count me out, say, a dozen atoms of hydrogen, or a dozen molecules of aspirin, you wouldn't be able to do it. They are so tiny that a dozen wouldn't be enough. In fact, atoms, molecules, and ions are so tiny that even 1,000,000 of them would be too small of an amount to weigh out on a scale. So instead, we go with the mole, which is Avogadro's number, or 6.02 times 10 to the 23rd. This enormous number is a much more reasonable number to work with when we're talking about atoms, ions, and molecules. However, you can have a mole of anything. You can have a mole of molecules, a mole of ions, a mole of single elements, such as atoms. You can have a mole of cars, or a mole of M&Ms, or a mole of t-shirts, right? You can have a mole of anything, because mole just means that there are 6.02 times 10 to the 23rd of those things in that mole. So again, one mole of anything is equal to 6.02 times 10 to the 23rd of that thing. Therefore, that's an equality. And because it's an equality, we can make conversion factors out of it. We can say that 1 mole of whatever has 6.02 times 10 to the 23rd of that whatever. Or we can say that 6.02 times 10 to the 23rd of whatevers are in 1 mole of that. We use this number to convert moles of a substance into particles. For example, if you have a half a mole of carbon dioxide, how many carbon dioxide molecules do you have? So if you have a half a mole of CO2, how many CO2 molecules do you have? Well, 1 mole of CO2 molecules is 6.02 times 10 to the 23rd. So if you take 0.500 and you multiply that by 6.02 times 10 to the 23rd, you get that there are 3.01 times 10 to the 23rd, or exactly half, right? A half a mole has half the amount of particles. Let's try another example. Let's say we have let's see here. We have 2 moles of aluminum, and we want to know how many atoms of aluminum that is. So 2 moles of aluminum. In 1 mole of aluminum atoms, we have 6.02 times 10 to the 23rd. So 2 times 6.02 times 10 to the 23rd will tell us how many atoms of aluminum. So let's try that. 6.02 times 10 to the 23rd times 2. In 2 moles, you have 1.20 times 10 to the 24 atoms of aluminum. Please be comfortable using your calculator and putting scientific notation in it. If you're not, please contact me immediately so we can talk about it. Okay? Let's take a look at something else. The chemical formula subscripts in a molecule specify two things. They're a ratio, so they specify the number of atoms of each element within that molecule. In the example here, aspirin has 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms in one molecule. But because it's a ratio, it also tells you the moles of each element in 1 mole. There are 9 moles of carbon in 1 mole of aspirin, 8 moles of hydrogen in 1 mole of aspirin, and 4 moles of oxygen. You can think of it just like with the word dozen. For example, if you have a dozen cars, please excuse my terrible drawing skills here, but if you have a dozen cars, those are wheels I'm drawing, by the way. If you have 3 cars, you have 3 bodies, right? The body of the car. You have 6 wheels. You have 3 windshields. You have 6 windshield wipers, right? If you had a dozen cars, you'd have a dozen bodies. You'd have 4 dozen wheels. By the way, how in the world did I get 6 up here? If we have 3 cars, 3 times 4 is 12. I was counting the 2 I could see. Anyway, if you had a dozen cars, you'd have a dozen bodies, 4 dozen wheels, 4 dozen windshields, and twice that many windshield wipers, right? So you'd have 2 dozen windshield wipers. It's the same thing with molecules. You can relate the number of atoms within a molecule looking at the subscripts, and also the number of moles within 1 mole of that molecule. So again, the subscripts in a formula show the relationship of the atoms in that formula and the relationship of moles of element in 1 mole of compound. So let's try another example. It says subscripts are used to write conversion factors for moles of each element in 1 mole of compound. For 1 mole of aspirin, the possible conversion factors are, well, let's take a look. We said that we are looking for conversion factors for moles of each element in 1 mole of a compound. So in 1 mole of aspirin, there are how many moles of carbon? Well, we said that 1 mole of C9H8O4 has 9 moles of carbon. That's one conversion factor. Or you could say that 9 moles of carbon are present in 1 mole of aspirin, C9H8O4. We could also say hydrogen. We could say that in 1 mole of aspirin, C9H8O4, there are 8 moles of hydrogen. Or we could say that for every 8 moles of hydrogen present, there is 1 mole of aspirin. Now you try that for oxygen. Pause the video if you need a bit more time. Okay, let's try it for oxygen. 1 mole of aspirin, C9H8O4, has 4 mole oxygen. Or for every 4 mole of oxygen, you have 1 mole of C9H8O4. Okay, well, let's put that to use. How many atoms of oxygen are in 0.150 mole of aspirin? Well, first, what do we have? We have 0.150 mole of C9H8O4. What do we know from here? We want to get atoms of oxygen. We know moles of aspirin. In order to pull out the atoms of oxygen, we need to look at the relationship between moles of oxygen and moles of molecule. Then we can look at the relationship between moles and atoms. 1 mole of aspirin has 4 mole of oxygen. But now we want to know atoms of oxygen. 1 mole of oxygen has 6.02 times 10 to the 23rd atoms of oxygen. So we have canceled moles of aspirin, and then we cancel moles of oxygen, and we're left with atoms. So let's put this in our calculator and see what we get. 0.150 times 4 gives me 0.6 times 6.02 times 10 to the 23rd gives me an answer of 3.612 times 10 to the 23rd. Now, sig figs. We count this and we count this number. We do not count the sig figs in the 4 moles of oxygen to 1 mole of aspirin because this is an exact number, counting number. So we have how many sig figs in this first number? We have 1, 2, 3. In the second number, we have 1, 2, 3. We should have 3 in our answer. So if we're going to round this, we would say 3.61 times 10 to the 23rd. In addition to being able to go from atoms to moles to molecules, we also want to look at the molar mass. The molar mass is the mass, or how much 1 mole of that element weighs. Since all of the elements have different weights, every element has its own special molar mass, as does every molecule. The molar mass of an element is its atomic mass expressed in grams, which makes this very convenient since the atomic mass is listed on the periodic table. For example, if you look at carbon on the periodic table, carbon has a mass of 12.01. That means there are 12.01 grams of carbon in 1 mole of carbon. Lithium, on the other hand, has a mass of 6.941, which means that 1 mole of lithium weighs 6.941 grams. Well, for an element, that's easy. You just look at the periodic table. For example, if you look on your periodic table, what is the mass of 1 mole of calcium? You can pause the video here if you need a moment to look that up. The mass of 1 mole of calcium per the periodic table is 4.078 grams. Therefore, there are 4.078 grams of calcium in a mole. Please note that periodic tables have small variations, particularly in how many significant figures they report. So your periodic table may have more or less numbers on it than the number I just mentioned. They all should be very close, though, as far as the actual value. What do we do, though, if we have a compound? A compound has multiple elements in it. How do we determine the molar mass then? Well, we multiply the molar mass of each element by its subscript in the formula and add up all the pieces together. So let's calculate the molar mass for lithium carbonate. In lithium carbonate, you have 2 lithiums. 1 lithium weighs 6.941 grams per 1 mole, but we have 2 lithiums, so we need to multiply this by 2. 1 carbon weighs 12.01 grams per mole. We only have 1 carbon in this formula, so we don't need to multiply this by anything. Oxygen. If you look at your periodic table, oxygen weighs 16.00 grams per mole. There are 3 oxygens, so we need to multiply this by 3. To determine the molar mass, we add everything up. So in your calculator, you would type in 6.941 times 2. Enter. That gives you 13.882. To that number, you are going to add 12.01. Now, to this number, which we are now up to 25.892, we are going to add the 16 times 3. If you are putting this into your calculator, please use parentheses around the 16 times 3 so as not to mess up the order of operations. You should get a final answer of 73.892 grams per mole. This is how many grams 1 mole of lithium carbonate weighs. Again, this is how many grams 1 mole of lithium carbonate weighs. Let's try another example. Let's calculate the molar mass of C2H6O. If we look at our periodic table, we see that 1 mole of carbon weighs 12.01 grams. But we have 2 moles of carbon in this molecule, so we need to multiply this by 2. Hydrogen if we look at our periodic table, weighs 1.01 grams per mole. There are 6 moles of hydrogen, so we need to multiply by 6. And finally, oxygen weighs 16.00 grams per mole. There is only 1 oxygen, so we don't need to multiply that by anything. Then we add these totals up. So, again, if you're typing this in your calculator, please be sure that you are following your order of operations. It is 12.01 times 2, which should give you 24.02. Plus, parentheses, 1.01 times 6, end parentheses, plus 16.00, which should give you a total mass of 46.08. Therefore, 1 mole of C2H6O weighs 46.08 grams, or the molar mass of this compound is 46.08 grams per mole. Therefore, if you had 2 moles of C2H6O, you would multiply that by 2 to determine how many grams you have. Molar mass conversion factors are ratios or fractions written from the molar mass. They relate grams and moles of an element or compound. For methane, CH4, using gas stoves and gas heaters, it is 1 mole of CH4 weighs 16.05 grams. This comes from what we just did. There are approximately 12.01 grams of carbon in 1 mole of carbon and 1.01 in 1 mole of hydrogen. There are 4 moles of hydrogen, so 12 plus 1.01 plus 1.01 plus 1.01 plus 1.01 gives you 16.05. From this, you can write 2 conversion factors. You can say that there are 16.05 grams of methane in 1 mole of methane, or you can say that 1 mole of methane weighs 16.05 grams. Let's try some more examples. A box of table salt, sodium chloride, NaCl, contains 737 grams of sodium chloride. How many moles are in the box? Well, let's take a look. We have a starting amount of 737 grams of NaCl. We need to know how many grams are in 1 mole of NaCl. If we take a look at our periodic table, we see that sodium contains 22.990 grams in 1 mole. And chlorine contains 35.45 grams in 1 mole. So 1 mole of sodium chloride weighs 22.990 plus 35.45, or a total of 58.44 grams. Okay, we need this in order to answer this question, 58.44 grams. So our conversion factor says that 1 mole of sodium chloride weighs 58.44 grams. We have 737 grams. We wish to know how many moles that is. So 737 grams divided by 58.44 tells us that there are 12.61, or with our correct figures, 12 significant figures, 12.6 moles of sodium chloride in the box. So you can impress all your family members tonight at the dinner table. You can go grab the box of Morton salt and say, hey, guess how many moles are in this box? I know how many. There are 12.6 moles. And your family will all look at you like you're crazy and they will all say, what are moles? And then you can get into teaching them what moles are. All right, example 11. A sample of water has a mass of 59.8 grams. How many moles of water are in the sample? So our starting amount is 59.8 grams. We need to know how many grams are in 1 mole of water. Again, if we look at our trusty periodic table, we will see that oxygen contains approximately 16 grams in 1 mole, and hydrogen 1.01 grams in 1 mole. There are how many hydrogens in a molecule of water? There are 2, so it would be 1.01 times 2, which is 2.02, plus 16 gives us a total of 18.02 grams in 1 mole. 18.02 grams of water in 1 mole. So if we plug this into our trusty calculators, 59.8 divided by 18.02, we will see that there are 3.32 moles of water in the sample. Now, the law of conservation of mass says that in a regular ordinary chemical reaction, matter cannot be created or destroyed, meaning there is no change in total mass from the left-hand side of the equation to the right-hand side of the equation. The mass of the products is equal to the mass of the reactants. Just like when we were balancing equations in a previous chapter, you must also have balanced mass. For example, in the chemical reaction of iron and sulfur, the mass of the reactants is the same as the mass of the product, Fe2S3. Consider the following equation. 2 atoms of solid iron plus 3 atoms of solid sulfur forms 1 molecule of Fe2S3. We could also read this as 2 moles of iron plus 3 moles of sulfur gives us 1 mole of Fe2S3. A mole-mole factor, which is going to be very important in chemistry. A mole-mole factor is a ratio of the moles for any two substances in an equation. So for this equation, we can say that for every 2 moles of iron, we need 3 moles of sulfur. And for every 3 moles of sulfur, we need 2 moles of iron. We could also say that for 2 moles of iron, we get 1 mole of Fe2S3. And for every 1 mole of Fe2S3, we must have had 2 moles of iron. We can also say that for every 3 moles of sulfur, we get 1 mole of Fe2S3. And for every 1 mole of Fe2S3, we must have had 3 moles of sulfur. These are called mole-mole factors, and they are very important. Mole-mole factor. Mole-mole factor. You will use these a lot the rest of this semester. So, how many moles of Fe2S3 can form if you have 6 moles of sulfur? Well, if you have 6 moles of sulfur, how many moles of Fe2S3 can you make? Well, let's take a look at our mole-mole ratio. Our mole-mole factor says that for every 3 mole of sulfur, we get 1 mole of Fe2S3. 6.0 divided by 3 gives us an answer. Well, in your calculator, it gives you exactly 2, but remember we're looking at significant figures, so our answer should be 2.0 mole of Fe2S3. Why? Because these mole-mole ratios are exact. These are counting. You do not look at these when you consider sig figs. This is the only thing with significant figures in it, so your answer should have the same number, or 2 moles. Okay, this concludes Chapter 7, Part 2. I look forward to seeing you in the next lesson. Have a great afternoon.